You first came across the cumulative distribution function back in the discrete variable module. Here we're going to reintroduce it in the context of continuous variables, and we're going to look at our traffic inter-arrival time example one more time and start with the continuous version of that, where we had the probability density function that looked like a triangular shaped distribution centered at 9 with a base that was 18, and its height was 1/9. Remember that total area under the curve had to be 1, so area of a triangle, 1/2 the base times the height, so 1/9 times 18 divided all by 2 gives us exactly an area of 1. That's great. Right, now, if we were interested in probability that a random variable was between A and B, then from an integral approach we go A to B ft of t dt. Not how I would probably actually do it in practice. Instead, I would look on the curve and see, is this something I can do easily just by the geometric shapes that are there? If not, well, then maybe I have to go do the actual math. Otherwise, I'll take advantage of the shapes that are available to us. Now, that's all well fine and good, but what if you don't want to do the math and you don't have a nice easy shape? And that's where the cumulative distribution function comes into play in some of its power for us. We didn't use it a whole lot when we introduced it before, but now we'll start to see more of its power. Now, a lot of people call the cumulative distribution function, see, it's a mouthful, right? They'll say CDF. And in terms of symbols, what they'll do is they'll use a capital F. So probability density is a lowercase f, capital F is the cumulative distribution function. And thou shalt never confuse the two or swap them back and forth, else you will create massive confusion for all kinds of folks. Right? So by definition then, ft of t, what that is the probability that a random variable is less than or equal to t. So we're going to look at what happens as we march along, and in essence, how does this area grow as a function of t? And from an integral standpoint, then that's from the lower bound up to t, and for elegance we use a dummy variable in that particular expression. Again, if I have to, I will evaluate this. I'd rather deal with the geometry, and if I can't do either one, I'll actually go to plotted values of this function, and sometimes that's a very easy thing to do. And in this case, I don't know if it's easy, but we can get some critical values just by looking at what must be the properties of this function. For instance, we do know that since our lower bound for our time was 0, that in this case, for all values less than 0, then the CDF is 0. There's no chance of having a value out there. We know also that something special happens here at 18. And if we were a live class with lots of students sitting out there that could respond, I'd ask the jump ball question, hey, what special thing has to happen out there? And somebody will recognize that, hey, at 18, we've reached the max area under the curve. The max area under a probability density function has to be 100% of the area. Okay, so that's a critical value that we have out there. And I say, well, anything else special that we know about? And you might think about it for a little bit and say, well, hey, you know, there is something special that happens here at 9, and it's not that it's the centroid, but rather notice that 1/2 of the area is on either side. So if that's the case, then it must be also true that at 9 down here, the CDF has to be 1/2. A curve has to pass through that point. On the upper end at 18, we don't have any more values, so that would be a slope of 0. We have a slope of 0 there. And I say, anything else special about this? And someone else would be clever and they say, well, hey, wait a minute. The slope, the first derivative of the cumulative distribution function, is the density function. And the density function is always positive. Can't have negative probability densities. So that means that this curve, as we go from one end to the other, always has to have either 0 slope or a positive slope. But it cannot have a negative slope because there's no such thing as negative probability. Very nice, I'd say. And I'd say, okay, anybody want to really step up the bar, potential bonus points here, tell me anything else that has to also be true. And someone is going to say, well, all right, wait a minute, this here is a straight line, and that's a polynomial of first order. That's going to be sitting in here, and although I could go find out what that equation is, I don't need to be able to determine some characteristics in this very specific case, and that is, if I integrate a first order, I'm going to get a second order. Oh, all right, so I have a parabola somewhere over in the left side, and then a different parabola over here on the right side, all because of the way our density function is up here. Very interesting. I say, cool, that's worth bonus points. All right, so now for the real bonus points, though, is that concave up or concave down? And we might scratch our head a little bit, but note, hey, look at this. As we go for every little additional delta t here on the left, as we progressively march over, that's bigger and bigger little delta area, right? And so we must be concave up. It must be accelerating up. And then over here, every little delta t is a little bit less as we go along. And so those little delta t's are slowing down as they pile up the probability, and it'll be concave down. Very nice. So there's our plot of our cumulative distribution function for this particular case. And its general characteristics are dead on, that you'll have start off at 0, you'll end up at 1. At some point you'll pass through the median. In the median, remember that's just the division between 50% above and below. Turns out in this case to also be where the center of mass, or the mean, is located. We always have either 0 or positively sloped curve, right? And the real nice usefulness of this is that, let's say I wanted to know what the probability was that t was less than or equal to 12 seconds. Right? Well, let's see, that would be right about here. And so I could try to go evaluate this, or I could come up to the curve, and if I plotted this actually to scale, we have it here, but if we had plotted it, I could just grab that right off. That would tell me what the probability is that t is less than or equal to 12 seconds. Right? Another way to do that is, because we do have a nice area to work with, is we could come up here and we could find all the area to the left. Well, while you're doing that, what I'm going to do is the simpler one. I'm going to find the area to the right, and then I'm going to subtract that from 1. Right? So probability of t less than or equal to 12 is also equal to 1 minus the probability that t is greater than 12. Stylistically, I flip-flopped here, and I put the equals only on one side. Now, again, for the continuous, it really makes no difference. For a discrete random variable, of course, it would. Right? Anybody want to do that math real quick? It's not actually too bad, right? Because 12, we get a difference of here a 3 and a 6 there, so it's 2/3 of the way from 18 to 9, which means that it's 2/3 of the way from here up to 1/9. So that means that that height has to be 2/3 of 1/9, or 2/27. So our math would be 1 minus 2/27, that's the height, times the base of 6, and that's the area of a triangle, so 1/2. Right? So 6 divided by 2 is 3, 3 over 27 is 9, so that's 2/9, and 1 minus that would be 7/9. Well, I sure hope that is exactly right, because if it's not, it's going to be recorded forever as it is wrong. You check me and make sure.